In this video, I'd like to talk about something called restorative forces. Some materials, if you deform them, they will not return themselves to their original shape. For example, soft clay. If you deform some soft clay, it will retain its new shape and not return to its original shape. Some materials do return to their original shape. For example, if you squeeze a sponge or a volleyball or a spring, when you release it, it will return to its original shape. In this PHYS simulation, we can see that if I put a cylinder on this spring, the force of gravity pulls down on the cylinder and accelerates it downward, but as it does, it deforms the spring it is attached to, which exerts a force that starts out at 0 newtons but increases in magnitude the more the spring stretches. That makes the weight stop accelerating downward. We can see here that the force of the spring equals the force of gravity in magnitude, and the cylinder is then held stationary. If I increase the mass, the force of gravity increases and pulls down harder. But no matter what I increase the mass to in this simulation, the spring, once it has been stretched to this new greater length, will exert a force upward equal to that larger force of gravity. When the relationship between the change in length and the restorative force is direct, it is known as Hooke's law. That is the same Robert Hooke who discovered that under a microscope, cork has a structure that looks like monastery cells. Note the picture on the right on this slide. The long coil spring looks like the one in the PHYS simulation I just showed you. There's also one at the top that is a 2D spiral coil. This relationship, Hooke's law, takes many forms. Right now we care about it in one dimension. I'd like to provide a couple of pointers about springs and other objects that follow Hooke's law. The phrase ideal spring means that the force restorative is proportional to the delta L, the distortion of the material. Meaning, the more you distort the material, the harder it pulls back to its original shape. Secondly, the spring in this picture has a length before distortion, where the restorative force is therefore equal to 0. That length is x. And then when the spring is stretched, its length becomes x plus delta x. It now has a non-zero restorative force. Be careful of the wording in any question to be clear whether they are giving you the length that the spring has stretched or the length that it has stretched to become. Thirdly, note that when the spring is stretched to the right, the restorative force points to the left. That's by definition, that's what it means to be a restorative force. Thus, in Hooke's law, there is a negative sign built into the mathematics. Do not let this negative sign throw off your equations. This negative sign is telling you that whether you have compressed or stretched the spring, delta x, to the left or the right, the restorative force will be pointed in the opposite direction. That's why it's called a restorative force. One more note I would like to make. An ideal spring can be stretched or compressed, either one, which is not true of all springs that we actually work with. Make sure when you are reading any given problem, you are clear on whether a spring is being stretched or compressed in the problem. That, of course, is a lot easier if a drawing is provided, and if it's not provided, you will want to draw one precisely to make sure that is clear. I did a little experiment to determine the spring constant of this spring. And the whole point of a spring constant is it's not a constant like the acceleration due to gravity, which is negative 9.8 meters per second anywhere on Earth. A spring constant is unique to its spring. So if a spring constant on this spring might be 8 newtons per meter, and you might have another one that's 70 newtons per meter. I guess in that respect it is a lot like the acceleration due to gravity, in that if you go to another planet you would have a different acceleration due to gravity. But my point is that a spring constant isn't a single value that you can look up. It's different for each spring. In order to do the experiment that I'm about to show you, I took this force sensor that is able to plug into the same software that I've been using for all of the kinematics videos. This force sensor just measures how hard you pull on the hook. So I set it up like this, and I'm going to pull on the spring and determine how much it stretches for each given force that I'm applying. I set up a graph that looks like this. It has the force on the y-axis and the position on the x-axis. That's a little bit different. Let me back up real quick. That's different from the one they showed you in the book where they had the force on the x-axis and the stretch on the y-axis. They did this because the force is the independent variable and the stretch was the dependent variable. I put it like this because we're going to find that it's much more useful to have it this way for at least 2 different chapters, including this one. So here's the experiment I did. I stretch the spring, I bring it back. Motion detector is on the right there, and it's able to determine therefore how much I have moved the cart. The cart is only there to make it easy for me to move for me to track the movement of my force sensor. How far the cart moves is the same as how far the spring has stretched. So I get this graph, it looks like this, and as I've increased the force, I've decreased the distance because of the way I have this set up. If I had set this up so that the motion detector was on the other side over by the spring, I would actually be measuring how much the spring stretched more directly. The way I had it set up is a little bit different. How much it stretched is still shown on here, but I have this negative slope instead of this positive slope, just because of the way I set up the experiment. The point of this, though, is that the slope is giving me a reading of 8.313 newtons per meter. The fact that it's negative because of the way I set it up is not as interesting as the fact that the slope is coming out in units of newtons per meter. That is the spring constant. That means if I applied 8.313 newtons, I should be able to stretch that spring a meter, which would definitely break it, so I didn't do that. But that can then be used to determine how much force was applied to stretch it 1 centimeter or 2 centimeters, etc. That constant applies to that spring, however I use that spring, as long as I'm not breaking it. I said there's a much more useful reason that we would want to study Hooke's law other than to note that some objects are elastic, and those objects sometimes follow Hooke's law, and that is something we will be getting into in a future chapter, and it looks like this. Simple harmonic motion is going to help us do a lot of things like model how atoms in a solid structure interact with one another. The bonds between atoms can be modeled as springs in a lot of cases. So that is our introduction to restorative forces, and I think at this point we just need some example problems.